Unit 6, Section 2. In these examples, we're being given that these different quadrilaterals are in fact similar and asked to solve for different angle measures and side lengths. So example 5, part A, we're given that MNPQ is similar to RSTU, and we need to solve for X, Y, and Z. Well, I'm going to start with Z, because that's our angle measure. And I see if I look at the similarity statement, I see that if I'm solving for angle R, that should be congruent to angle M. So I know angle M is 115, so that means angle R must also be 115. So I know right off the bat that Z equals 115 degrees. Because remember, for similar polygons, we know that they have congruent angles. They're the same. There's no proportions there. But now we're moving on to side lengths, and that's where our proportions and our ratios are going to come in. So I see that what I want to find is a ratio that I'm already given both parts to. And so I see that MN, which is the first two letters, should be proportional to RS, which is this piece, and I know both of those. So I'm going to set it up so I have 18 over 30 as our proportion, or as our ratio, and I want to set that up as a proportion to solve for these other pieces. So if I want to solve for X first, I'm going to look at this side, NP. I'm going to say X over, and NP should be proportional to ST, which is this piece right here, so X over 25. And once again, all I have to do is cross multiply, so 18 times 25 should equal 30x. I can solve, so x equals 15. And that's all it asks me to do for there, and then I need to solve for y as well. But it's a similar thing. I'm going to use my 18 over 30 ratio again and set up my proportion. This time, I start with a smaller one. I know that QP is 15, and that should be proportionate to TU. Once again, I can check my letters in my similarity statement to make sure it lines up, and I see PQ and TU as the last two letters of each. And I have my smaller over my bigger, so 15 over y. I set up to cross multiply, so 30 times 15 equals 18y, and I solve for y to get 25. So that's how you go about solving for missing side lengths and angle measures. Let's do another example. Here we're given two what it looks like rectangles, or quadrilaterals, I guess, just to be similar. So ABCD, that big rectangle, is congruent, or not congruent, similar to AMNP. So it wants me to find some pieces of the side lengths. Well, I know that AP is 40, and I know that MA is 30, and I also know that CD equals 45. Okay, so that's going to be key. So I'm starting, it wants me to find BM, which is this little piece right here. Well, for this, instead of using any proportions, I'm really just going to use parts to whole to my advantage. So I know that AM plus MB should equal the whole thing, which is the same as CD. So I know that AM is 30, and I'm solving for MB, and then I know that whole side length is 45, since that's a rectangle. And then I can solve for MB to be 45 minus 30, which is 15. Okay, so I'll write that in. Now it wants me to solve for BC. So that's this whole piece up here. And I can't really do anything with parts to whole because I don't know what that little PD piece is at the bottom, so I think I'm going to use some proportions here. So if I could figure out what that whole BC is over MN, because that's the similar piece. Once again, I can check my letters, BC and MN. That proportion should be equal to, well, I'll use what else I know, which I could do that whole, if BC and MN are the lengths, I can think about the widths. So I can do the big width, which is BA, over MA, the smaller width. And I can set those up with what I know. So I'm solving for BC, and I don't know what that is, but I do know MN is also going to be 40, because AP is 40, and it's a rectangle. BA is 30 plus 15, or I also just know it's 45. And MA is that piece that is 30. And so I set that up to be BC times 30 equals 40 times 45. Therefore, BC equals 60. All right, I'm almost there. It just wants me to solve for PD. Okay, so that's this little piece right here. Well, since I know essentially all the other pieces, I'm going to use parts to whole again. Since I know that all of AD, this whole thing right here, should be equal to AP plus PD. And I know the whole thing is the same as BC, which is 60, because I know it's the same as this length, which I just solved for. And then AP is 40 plus PD, so therefore PD must be 60 minus 40, which is 20. So those are the three pieces I was looking for. So we can use the fact that two polygons are similar to solve for different side lengths and angle measures. And we have one more example in the next video. Unit 6, Section 2, Video 4. This is our last example in this section. And this is using a lot of what we know about ratios and thinking about what that means for the perimeter, the area, and later even volume. So this is a little bit of a precursor to the next section. Now on the previous page, I'm just going to write it here again, we're given that ABCD is similar to LMNP. So we can use that to find what those ratios should be. And I'm going to give you a quick note that K, that proportion that we use a lot, or the ratio, the scale factor, that's the word I'm looking for, the scale factor, we usually use it for new over original. And so we have to decide kind of which way we're going. Which one is the new one and which one is the original one. So if I'm thinking about this big one as being the original, and this one is the new one, that means I would think about taking this one and shrinking it down. So that would mean I'd put the new numbers, so the new side lengths over the original side lengths, and it'd have to be a fraction because I'm shrinking it down. So I put the smaller number over the bigger number. And if I was doing it the other way around, I would have a bigger number over a smaller number, so it means I would have a number greater than 1, or I'd be blowing it up to be bigger. But here I'm going to think about shrinking it down. So it asks what are the ratios of the side lengths. So K equals new, so we'll do a width first, 30 over 45. So there I did AD over LP, and I know that those are similar because I can look at my similarity statement, and I can just use just those sides. I don't need to worry about 40 over 60 because it should be equal. And I just want to simplify that down. And I can simplify that down to 2 over 3. So that is my scale factor. That's the factor of what I'm shrinking down that bigger rectangle into a smaller rectangle. Now it asks me to think about the ratio of the perimeters. So once again, I'm going to do the perimeter of my new polygon over the perimeter of my original polygon. And perimeter we know is the distance around a polygon, so I add up all of the side lengths. So I'd add up 30 plus 40 plus 30 plus 40. And I'd do that for the original as well. I would do 45 plus 60 plus 45 plus 60. And if I add those up, I get 140 over 210. And I can get rid of, or divide both those by 10, or get rid of the 0, so I have 14 over 21. And then those actually both can be divided easily to be 2 over 3. So that is the ratio of the perimeters, which we see is the same as my scale factor of the side lengths. It doesn't change. But we're going to notice something a little different when we look at the ratio of the areas. So once again, I'm going to do the area of the new over area of the original. And I know that area equals length times width. So area of the new would be 30 times 40. And the area of the original would be 45 times 60. And I get that to be 1200 over 2700. And I can simplify that down to 12 over 27, and then simplify that down, divide those both by 3 to get 4 over 9. And I can't simplify that down any further. And so I see that the scale factor for the ratio of the areas is different than the ratio of the perimeters. And so this last question asks me to look at that and decide, what do I think is the relationship between those? So I see that the ratio of the sides, well, that's 2 over 3. And the ratio of the perimeters, well, that was also 2 over 3. So those are equal. Well, but the ratio of the perimeter, which was 2 over 3, and the ratio of the area was 4 over 9, and those were not equal. So think about, what do you think happens to the ratio of the side lengths of the perimeter when it becomes a ratio of the areas? What could I do to figure out what the ratio of the areas is if I just know what the ratio is for the side length? So we're going to talk about that in the next section, but I encourage you to begin to think about how could we figure that out and what is that relationship. And this concludes section 2.